So when you use eigenvalues, you like to write a matrix in factorized form, right? So we talk about maybe writing a given matrix A, right, as we wrote something like S, lambda, and maybe S inverse, or maybe the S inverse was first and then lambda in the middle and S at the end, right? And this works fine if you have a square matrix, and then the factorization is also square matrix, and then the middle, the matrix is square, but really is a square in the shape of diagonal, okay? So this here is what you would call the diagonalization, or, right, those were the words, diagonalization. Also, this is called eigen decomposition, okay? So the idea is that you decompose the matrix, and the decompose or decomposition is the factorization, okay? But it's a factorization with a very specific structure. Now, there is this other family of objects that they're not called eigenvalues, but they are inspired by the eigenvalue eigenvector equations, and they are called singular. Instead of eigen, they're called singular values. And they're very useful for matrices that are rectangular. So the idea is similar, that you like to express the rectangular matrix. This could be expressed in a number of ways. You could have matrix that looks like this. Let's see, this could be of the same dimensions here, and then there's a square in the middle, for example, and this one could be multiplied by another square, something like this, okay? So the important thing here is that the so-called singular values are going to be collected in a matrix that is also in the middle. And because this is a factorization, then that factorization typically is referred to as a decomposition, okay? It's typically referred to as a decomposition. So that word decomposition, I wanted to maybe bring this to attention. Since we're talking about decomposing, so you could think of this as zombie math, something that looks like this, right? So very good features you see there, especially around, you know, in the mouth or something, and things kind of, I don't know, decompose, zombie math, decomposition, eigenvalue decomposition, singular value decomposition, okay? That's kind of what we are considering. So the eigenvalue decomposition is based on equations of this type. Last time we talked about if you have eigenvalues that are not repeated, you call them, they're different, distinct of each other, and under those conditions, then their corresponding eigenvectors together form a set that is linearly independent and has a lot of properties, right? So under those conditions, then you can write the original matrix as in the decomposition, the eigenvalue decomposition, which is that also what you call diagonalization. So if the matrix is rectangular, you could come up with another factorization, which is considered a decomposition that uses singular values. And here you want to associate, just like what you did with eigenvalues, each of those values with not just one vector, but in fact, two vectors. And these vectors are going to be, you know, the value is going to be typically denoted as sigma, and then the two vectors associated with that one value here denoted as u and v. And these vectors are important because each of them is, okay, well, let's say more. So when you say one matrix, two vectors, one value, this is in the spirit of the eigenvalue eigenvector equation. This relates a matrix and the two vectors v, u, and then this one value sigma. A star is something like the transpose of the matrix, but is an operator that involves transposition and complex conjugation, okay? And so it has a fancy name, Hermitian. You can call it Hermitian operator or Hermitian transpose or conjugate of a matrix, okay? And so, so both of these equations are needed to define what V, U, and sigma are in relation to the matrix A. So you would collect all the little, you know, all the values, which are here called sigma, you would collect them in a matrix called big sigma, and you would collect those vectors U into a matrix you call big U. So the U vectors are columns, and you stack them into a matrix big U, And similarly for the V vectors, you call them V1, V2, also, all the way through how many columns you consider. Stack them into a matrix called V, and so this matrix V and U and the matrix sigma are basically what you use to write the factorization. That's where you're heading. The U and the V matrices are important because they are called unitary. So they have the property that the columns are orthogonal, and that also columns that have norm equal to 1. So when when you consider that star operator, which is basically the transpose, but like Hermitian or conjugate, complex conjugate transpose, then you find that in simpler terms, if you were just dealing with
star U I.
What?
Is U star U I, or is that?
Is U star U
I, like the identity matrix?
No, but they are, so you could think of the star as a transpose. You could, what this equation here says is like U transpose equals I, and from U transpose equals I, it's, maybe that's what you're thinking here. What that tells you is that the transpose is the inverse of U. So it's not that U transpose or U star is the identity, is that the transpose is the inverse. And also that the matrix U is the inverse of the transpose, So that's a neat feature. That's also something you have here. V transpose V is a neat feature of the columns that you use in this factorization or decomposition. So the values sigma 1, sigma 2, all the way through sigma n, they also have the property that they're not, well, I guess you could say they're complex with 0 imaginary parts. So they're actually purely real numbers, and not only they're purely real numbers, they're non-negative real numbers. So they are either 0 or positive, And so ultimately, you like to write, this is what we would call this so-called singular value decomposition is precisely this factorization. So
What
you're,
is
yeah.
What is U? What's this vector U? Is U a matrix or?
Yeah. So in this page, U is a matrix. So in this page, U is a matrix that is formed by U1, U2, U3, all the U's. I don't know how many columns we're saying here. We have U sub P.
How do you calculate A star?
So U star, I went through that very fast, and we're not really using the matrices with complex entries right now, but U star is the transpose of the conjugate. It's also the conjugate of the transpose. So the star is another operator, is another matrix operator or matrix operation. Very similar to the transposition, but it uses conjugation of complex numbers. When you're using matrices that have 0 imaginary parts, when your entries are purely real numbers, then the star and the T, like the adjoint and the transpose become the same. They're exactly the same. So for practical purposes, wherever you see star here, you're really dealing with transpose. That's what that star is. Okay, so, and as you have, by now being very clear, computing eigenvalues and computing eigenvectors, is it easy?
These aren't even eigenvalues and eigenvectors. They're like special.
So in general, not exactly eigenvalue and eigenvalue computations could be handled by hand, provided you can rephrase or refactor some of those polynomials into polynomials that involve degree 2 quadratic polynomials. Other than that, even computing roots of higher order polynomials is a process that by hand is quite cumbersome. It's very, so singular values then similarly are quite a task to do by hand, but let's just to give you some idea, because what we're going to do is compute these things with algorithms, with implementations, okay? So here's the 3 by 3. So instead of using the start, instead of using sigma, I'm gonna write S, right? So I'm writing here my notes S. That matrix S is a diagonal. So the idea is that here you have sigma 1, sigma 2, and sigma 3. Okay, so that's what S collects. It's a diagonal matrix. Sometimes it's a diagonal, in this case is square, but sometimes it's a rectangular kind of diagonal matrix. It's rectangular, so it's the top part is diagonal and the lower part is has rows of zeros. And then the matrix V here, so what we were calling those vectors, this would be V sub 1, this here would be V sub 2, and this here would be V sub 3, right? And similarly, this here would be U sub 1, this here would be U sub 2, and this here would be U sub 3.
So how do you derive the singular values? Like, let's just say that you're just given matrix A and you're asked to decompose it in the form U, sigma, and the Hermitian transpose of V. Let's say you're asked to find those 3 factors. How would you find the singular values?
So the question is, how do, like with eigenvalues, you have an idea. First, you have to compute the eigenvalues, doing the characteristic polynomial, and then finding the roots. And that you're almost able to do that by hand sometimes, by hand and with some help. But then you use each eigenvalue to evaluate into a new matrix and compute the basis of a null space, and that's how you compute eigenvectors. So that process for eigenvalues is almost by hand or by hand enhanced with a little bit of technology. That's for eigenvalues and eigenvectors. So the question is, how do you do something similar for singular values and their column vectors, the U's and the V's? You know, how do you come up with this? That's what you're wondering. And my answer is, just wait, give me another 5 minutes and I'll show you. That's what we're gonna do with algorithms, okay? So